Last week, we discussed the question of what you can answer your friends if they ask you what you've learned in this course. Today, we are going to forward the very same question to our neural networks and ask them, what did you learn? Welcome back to another edition of the Applied Deep Learning course. Today, we're going to talk about explainable AI and see if we can make some sense out of what our neural models learned and if we can get some meaningful explanations from them. As usual, please head over to Koul now and see if you remembered what we talked about last week and if you can answer the short questions from our weekly quiz. Last week we talked about how we can serve models, and the options that you basically have for serving neural models are pretty much the same as with every software application. You can distribute it as executables inside of a Docker container or directly as an application as a service to users, with the simplest way of distributing your work being that you just dump your trained model onto disk, and then you give someone else access to that trained model and they can load the weights and recover the model and then use the same tool chain that you've used for training the model and then reproduce your results. Which initiative makes an attempt to make AI tools more interoperable? That would be ONNX, the Open Neural Network Exchange, which is a set of companies that tried to sit together, define a way how you can export and import neural networks in such a way that you can switch from one tool to another one. What tools you have for running neural networks in the browser is also, I think, actually getting a longer and longer list by the day, but there are some really popular ones, namely TensorFlow.js, ONNX.js, but also some other ones like ConvNet.js, Keras.js, basically all of them relying on some sort of JavaScript in the frameworks. We also talked last week about some performance improvements that you can use for training your model in a better way and in a faster way. And the question was, how can you improve specifically the data loading performance? So we talked about prefetching, meaning that we didn't have to wait until our network processed one sample before we load the next sample from disk, but that we can basically do this at the same time. So we have a background process that kind of just constantly loads samples, and then we have our neural network that takes samples from that worker whenever it finishes one sample, and therefore we can kind of decouple this and try to avoid bottlenecks in our data loading pipeline. We can parallelize this process. We can cache data that is very expensive to compute, or we can basically distribute our entire training to not just train on one GPU, on one machine, but actually train on the whole server farm of machines, and that way speed up training and be able to train on much bigger data sets efficiently within a reasonable amount of time. Why can we use 16-bit floating points instead of 32-bit floating point weights for our neural networks? The answer is that most of the time we don't need those very large values that 32-bit floating points give us, or even sometimes 64-bit. Neither do we need the precision that they give us. That means we are operating in a space where you can approximate your numbers with a lower precision. Of course, we're losing some information there, but usually, statistically speaking, and for our neural networks, we have millions of weights. Losing some numbers behind certain comma is not that much of an issue here, so we can cope with that, and by reducing the amount of digits that we need for our floating point numbers, we can significantly reduce the model size, we can reduce the weights that we have here and how we represent those weights, and then ultimately speed up training by having two numbers compute at the same time, two 16-point numbers in one 32-bit register in our graphics card. Lastly, we talked about the lottery ticket hypothesis and how we can exploit it last week. And the idea behind this lottery ticket hypothesis is that when we have a randomly initialized dense neural network, that it contains a subnetwork that can be trained to be performing as good as the complete dense neural network. And we would say that these neurons that you can also train in isolation and in the end will perform equally well, have won the initialization lottery. And you can find these neurons, those tickets, those winning tickets, by pruning the network after you did some initial training and then retrain or partially retrain your network only with that subnetwork. Now to this week's topic of explainable artificial intelligence. This is a really hot topic, and it is understandable that whenever we train a neural network and it performs a certain task, we would like to ask the neural network, why did you do this? How did you come up with that conclusion, so we can understand whether it made sense or whether it might have an issue inside and it just accidentally created the right output. It basically boils down to the question, why should we trust a model in the first place? And if we had some explanations, we could help users to make educated decisions, to choose between competing models. So we can say, okay, this model has more to it, takes a bigger set of reasons into account why it made a certain decision than another model. Or say why a model might be untrustworthy. Remember back the classification of melanoma, the network predicted, like the number that we got from the network, the training precision was quite good, but it was absolutely untrustworthy because it was not looking at the thing we wanted it to look at, but at the ruler that was also in that image. So having that in the back of your mind and being able to ask a network, show me where in the image you focused on and why, and ultimately then why you made that decision, can really help us to detect and eliminate such errors. And last but not least, we are curious. We really want to understand what is going on in the model. We want to understand and maybe learn something from the model. If you think of a doctor that is making a diagnosis on some X-ray scans of your chest, the neural network can learn to look at specific regions, and the doctor might actually learn something. Maybe he hasn't seen that particular shape before, but the neural network has seen millions of examples before. So the doctor can then go to the patient, check it, and say, oh wow, I have to update my mental model as well, because this particular shape, I haven't seen it before, but it actually caused an issue in that patient. So we can also learn something from our neural networks. The problem is that with most of the models that we discussed in this lecture, they are pretty much this. They're a black box. And that black box is troubling many people. They want to use this, they see that it performs well, but if they have no idea what's going on in the inside, it can be hard to build up trust to such a model. So we want to see how we can take a look in that black box today and better understand what's going on in our neural networks. Before we dive into the technical details, let's clarify some of the terminology so we speak of the same things when we talk about explainable artificial intelligence. First of all, interpretability is the degree to which a human can understand the cause of a decision. So it's like how well can we as a human, if we see the same input, predict something and whether that confirms with what the model is predicting as well. So we see the same thing that the model sees, and then we can predict what the model is going to say. That would be interpretable. So it's a passive characteristic of a model referring to the level at which the given model makes sense for us as human observers. In contrast to that, explainability would be any action or procedure taken by the model to explain the intrinsic functions and the details of its inner workings. So if it has the intent of clarifying that inner behavior, that would be called explainability. And in contrast to interpretability, explainability is an active characteristic. So the model is actively trying to clarify and explaining its internal behavior to us. And an explanation, finally, is the collection of reasons the model can give us to understand why it has taken a certain way and make its functions clear and easy for us humans to understand. Why do we need interpretability and explainability at all? I think I already stated a couple of reasons, but speaking more about the technical reasons, a single metric that we all thought for our models, that when we train a model, we define a certain performance metric, that we measure our performance. That single metric might be incomplete. It might be an incomplete description of most real-world cases and most real-world tasks that we are training our models to operate on. So the average performance, average precision, for example, for object detection is a good summary, but it doesn't capture all of the details. It doesn't capture how it took certain features into account to perform certain tasks, or it doesn't tell us whether it's working better for big and worse for small objects or the like. We have to come up with more metrics and more explanations. And especially when we think about these aggregated metrics, they don't give us specific explanations for individual observations. So if we have one particular observation we want to learn more about, the average precision doesn't help us here. So the correct prediction usually only partially solves the problem. So we often might want to have additional explanations how it came up with that particular explanation. Especially in safety critical applications, I would say it's most important to understand what are those main features that it considered to make a certain decision. If you have an image classifier and it classified an image as a bicycle, it would really make sense to see and understand that the model looked at the two wheels and not at the background, which, I mean, you might take a photo of a bicycle outside, so you might have a green grass where it's standing on, but the network should not learn to look at the green grass, but at the two wheels. So that can help us to understand this much better. And then we can also make sure that the network, so if the network learned to take a look at the wheels, we can make sure that it also works when it's partially occluded. If some bags are standing in front of the bicycle, that it still can classify that bike. For safety critical applications, we might even have some laws and regulations that say we must be able to audit that system and debug it in case of failure. We want to inspect what led to that particular decision in case something goes wrong, because human lives are at stake here. We're also very curious, so even if we accept this, we would still like to learn why it did a certain, why the model predicted a certain outcome. And I think it's especially interesting if that prediction contradicts our mental model. Think back of the doctor that did not see a certain issue in the X-ray image. Well, the model might have contradicted his mental model because he didn't see anything, but it then helped him to learn something new from that. And last but not least, those explanations help us to manage social interactions and increase acceptance of machine learning models. If we can if the model can explain itself, we might say, okay, now I can trust you because the reason you gave me made sense. Or distrust the model if the reason that it's giving is making absolute nonsense. That is also an important thing to state and be able to tell the user. If the outcome is not trustworthy and the user should refrain from using that particular prediction, that can be very helpful and build up trust. If a model can say, well, I have a prediction for you, but I'm not certain of whether it's a good prediction or not, then the user can say, okay, I'll take over here. There is a fantastic movie called Big Hero 6. I'm not sure if you've seen it. So let's take a quick look how AI in medicine could look like in the future.
Ow! Ow!
Hello, I am Baymax, your personal healthcare companion.
Hey, Baymax, I didn't know you were still active.
I heard a sound of distress. What seems to be the trouble?
Oh, I just stubbed my toe a little. I'm fine.
On a scale of 1 to 10, how would you rate your pain?
A 0? I'm okay, really. Thanks. You can shrink now.
Does it hurt when I touch it?
It's okay. No touching. Ow.
You have fallen.
You think? Ow.
On a scale of 1
Ow.
on a scale on a scale
No.
on a scale of 1 to 10. On a scale of 1 to 10, how would you rate your pain?
0.
It is all right to cry.
No.
Crying is a natural response to pain.
I'm not crying.
I will scan you for injuries.
Don't scan me.
Scan complete.
Unbelievable.
You have sustained no injuries. However, your hormone and neurotransmitter levels indicate that you are experiencing mood swings, common in adolescence. Diagnosis? Puberty.
Whoa, what? Okay. Time to shrink now.
You should.
Coming from this very nice clip of Big Hero 6, what are the goals that we want to achieve with explainable artificial intelligence? So we would like to be informed. That helps us to make some decisions based on the inner workings and some simpler terms to understand what's going on here. Because the modeled problem often is not equal to the problem that humans have to solve, and therefore it can really help us to understand the problem, the underlying problem, and how the machine worked better if it is giving us some explanations. We would like to have some transferability. We would like to reuse knowledge from one problem and transfer it to another problem to understand also how well this works and what the limitations are of this transferability. We've already seen this when we split our data set into a train and a test set, that during training we wanted to only see the partial piece of the information and then see how it performs in the real world by running it ultimately on our test set that the model has never seen before. However, I should note here that not every transferable model is explainable though, so keep that in mind. Fairness is especially important if you have a machine learning model that is affecting regulations and our everyday life in such a way that we wanted to not discriminate against protected groups. So if you have a face detector, you would want that it works equally well for every person on the world. It shouldn't discriminate against blacks, for example. It should be able to find and be able to read people from all different ethnicities, and it shouldn't discriminate against certain groups. Privacy is also very important, and especially in Europe, this is a very important topic. We want our sensitive information to be protected. So the dystopian example would be that a machine is selling, like trying to come up with an assignment who to sell ads to. And the dystopian example would be that you're selling casino ads for gambling and you show them to pathological gamblers that cannot control their behavior, or you're sending someone diapers because you think they're pregnant, or sending them some other baby commercials, even though they might not know it themselves yet, but just from their behavior. And having some explanations on how this works, we can actively prevent that discrimination. Confidence is quite clear. We want to inform the user about the confidence of the predictions. We want to be able to say, I'm certain that this is the true output, or the model maybe backing off and saying, oh, I'm not really sure whether this is true or not. Reliability, meaning that whenever we change our input a little bit, it shouldn't lead to large output changes. We had this with the adversarial examples, if you remember, where we added a little bit of noise to our images and then completely destroyed the prediction of our neural network. Causality is maybe the easiest thing to understand here. We want to be able to find causal relations between our inputs and potentially our outputs. And of course, we want to be able to trust our model, because a system that can explain itself is much easier to trust, because we can understand the reasons it was taking into account for taking a particular decision. And last but not least, accessibility, where we would like to lower the barrier for using machine learning models by giving some explanations. Artificial intelligence has seen a rise in popularity, and this area of explainable AI has followed suit with a few years kind of behind, but it's becoming more and more popular in the last few years, and already this year we've seen many papers on this coming out every week, every month, and on all the big conferences there are several papers that you can find specifically tackling explainable AI. It might have different terms how it's being referred to, but you can see already from this graph that it's gaining popularity. There is one underlying issue with machine learning models in general, that the tendency is, when we draw the accuracy on one axis and the ability to explain itself on the other axis, there are models that we can understand very easily, like decision trees, but they tend to not be that accurate, especially for very complex problems. And we've seen that we can move towards this space of having more accurate models, but we're sacrificing the explainability along the way. And the community agrees that there is this negative correlation between explainability and accuracy. So the holy grail would be to find models from that area here where we are explainable and highly accurate. Currently, the most accurate models we have for many real-world problems are based on neural networks, but they are hard to explain, so we would kind of like to shift them maybe further down the explainability axis to get some more insights into them. And the first way how we can do this is by taking a look at how machine learning models can be explainable at all. And how we can achieve explainable AI would be either by having a transparent model that we can simulate, decompose, or that is transparent by definition algorithmically. or what we do most of the time with neural networks, to get some explanations after we've trained our model. That would be post hoc explainability, by getting some text explanations, visual explanations, or explanations by sample or by simplification. The transparent model, let's take a look at an example for that so it becomes a bit more clear what those three categories would be. For simulatability, it would be the ability to simulate or think about a certain model by a human, so strictly think about it. And if the system has certain rules, in this case we have certain mathematical functions, then we can start to run thought experiments. We can say what happens if that variable is bigger than the other variable. And then we can compute this and simulate this and take a look at what the outcome is. So we can understand this a little bit. Decomposability is the ability to explain each part of the model. So we not only want to simulate it, we want to dissect it and take a look at the individual components. We want to investigate the inputs, the parameters, and the calculations that are performed on those inputs on its own. In this case, we decompose our model here, for example, into saying the input variable x1 is the weight, the input variable x2 is the height, and the input variable x3 is the age. So we understand our inputs very clearly, and then we decompose the individual functions and the individual parts. And the third part here is algorithmic transparency, where which is basically the process by which decisions are made in this machine learning model. They should be easy to understand by humans. Linear regression is an example that is easy to understand. It's one line, and everything that is to one side of the line goes into one category, and everything that's on the other side goes into another category. Because we can now understand this error surface, and when you think about deep neural networks, we also have linear regression here internally, but the problem is that it's very, very complicated, and our loss landscape is it's not as clear and easy to understand and interpret. That's why we need these post hoc explainability methods, where we kind of get some explanations after we've trained a model that for us is a black box model. For example, we want to get some text explanations that say, well, that basically represent the functioning of the model. Like here, the output for xi is yi because of this particular condition. We could want to get some explanations by simplification, where we rebuild a system based on the trained model, but that rebuilt model is much simpler than the original model and more understandable. We will actually see one example for this later on in this lecture. Visual explanations is probably one of the things you can understand most easily by just saying, okay, I have an image problem from a visual domain, and the network should just point me to where it looked, or point me to where it thinks something of interest was going on. Local explanations would be segmenting and explaining parts of the solution space. Feature relevance explanations are assigning relevance to its managed variables, thus understanding the sensitivity of the output given certain variables. And of course, this is an indirect method to explain a model, and the final way to have explainability that I am doing constantly in this lecture is give you examples. So explainability by example. If we can ask the model, give me examples for a particular class of outcomes, then we can also understand whether we are doing the right thing here or not. Most of the traditional machine learning models have the properties that we can simulate them, we can decompose them, or they are algorithmically transparent by definition. So we don't need this post hoc analysis. And bear in mind that those check marks here come with an asterisk. So if you want to understand how and under which conditions these models fulfill these properties, please take a look at the paper. But the most important thing that I want to point out here is that the more complex machine learning models like support vector machines or deep neural networks do not share these properties. They cannot be simulated that easily, they can't be decomposed, and they are definitely not transparent algorithmically. So we need to employ some of those post hoc analysis methods. Because the problem really starts with big data that is more complex and where we have more dimensions, and a lot of the correspondences that happen are very intricate in our model. Possibly the simplest way to look and get some sort of explainability would be saliency maps. So what is a saliency map? Saliency, the concept saliency, when we talk about this, we talk about the input features that affect our output the most. And if we can get those input features, we can visualize them in a heat map. And if we visualize it, that's what we would call a saliency map. For images, saliency would capture the unique features, in our case pixels, of the most visually alluring locations in the image. Basically saying where it took a certain piece of information and where it should look at, which makes a lot of sense if you have a visual computing problem where images are being processed. In these examples, you can see that those heat maps, they're displayed as black and white images with white pixels, or something that being more white being more important. So we have this dome, we have a tractor and some fish, and you can see that the network did actually learn at those objects of interest and not at the background. So that's what the salience map is giving us. To compute such a saliency map, there is a kind of vanilla gradient algorithm that is the easiest way how we can do this, and it works the following way. We do a forward pass with some data, and then we compute our gradient by doing a backward pass. You know, we get something to the output, and the same way how we train our model, so we're doing this backward pass now, we pass that sample back all the way to our input, we capture the gradient, and then we just take that gradient. Remember, the gradient tells us in which direction we should go. It tells us which features also are relevant for a particular sample. We take this and render it as a normalized heat map. In this example, we can visualize this classification of the digit 3 in such a way that it shows which pixel contributed to the decision of making this in a very strong way. Those would be the red or dark red pixels, and all of the negative weights that made a decision against this would be then the dark blue. So kind of high negative values are near blue, high positive values are near red. So the gradient, remember this, tells us basically for every amount you change this particular input pixel, I change the output probability for a class this much. And I think this is a really good example, because the digit 3 and the digit 8 are only different in kind of closing those two loops. So it makes a lot of sense to say that there is something going on in that loop, and if we had changed that information, it would likely become an 8. So it makes sense that that part of the image has a deep blue color here. Let's take a look at a concrete example how we can create such saliency maps on our own. As usual, I'm now in Google Colab, and you can also try this experiment on your own afterwards at home and take this as a base. What I'm doing here is I am performing image classification, and I'm using a pre-trained model, a VGG19 model, to perform some image classification. So we have an image here of a kitten. We're downloading a pre-trained model because the saliency map takes an already trained model. Let's view this image. So that would be the input that the network is seeing. Here we have some pre-processing of normalizing our model. And now what we can see is this part of the code here. We do the same pre-processing that every input sample also got when it was trained, that model. And then we enable our gradient that it is being recorded, which this is important for PyTorch, otherwise it wouldn't record it, because when we're switched to the evaluation mode, where model weights are no longer updated, we automatically disable the gradient as well. Like, why should we record it if we're not intending on updating the weights? So we have to enable this again. And then we do exactly those 3 steps. We take our input sample, we run it through the model, then we compute the outcome, so to speak, here, where we basically just accept whatever the maximum class was and say, okay, that was our actual score. And then we run our backward operation on that sample and ultimately just take the gradient that we obtained, that is accumulated when going all the way back, and render it in this heat map here. And now you can see that from this kitten and this heat map where the most salient features were that led to this classification of it saying that this is a cat. And as you can see, it makes sense that it looks kind of here in the face area, maybe the nose, also the ears here, the pointy ears are important. And I think this is a great confirmation of how we as humans would probably also understand and learn and reason about that image. We would take a look at, not at the background. The background is quite unimportant, but we look at the pawns, like the face and the fur, of course, the entire body of the object. So that makes, I think, a lot of sense. And this is the easiest way how we can create such saliency maps that already give us some insight into where the model is actually looking. The next method we're going to take a look at is called Lime. And instead of just visualizing the weights of an individual input, we can also use so-called perturbation-based methods where we not just take an input and pass it through, but where we actually start messing around with our input and then watch what happens in our model. LIME stands for Local Interpretable Model Agnostic Explanations, and that means that local, it's for a specific observation instead of showing global trends. So it's not the average precision, it's for one particular sample we want to get some explanations. It's interpretable by trying to explain which features it used to come up with a certain output, and model agnostic being in such a sense that it can be applied to basically any black box model. It doesn't have to be a deep convolutional neural network. You can apply this to any black box model. So this is an example from that paper that shows a Labrador and seemingly being able to play the guitar. And you can see that when you ask for specific concepts that it showed in that image, it will point out those regions. How it works is the following. We are now in the domain of perturbation-based methods. So we take our sample and we start messing around with it. We create fake data by changing that one individual observation. Then, once we created some fake data, we compute the distance between the generated data, our fake data, and the original observation. Now we know how much sort of we changed one of those fake samples and how close they are still to the original sample. Then we take all these samples, our fake samples, run them through our model and make predictions. And once we ran our predictions through the model, we can try different combinations to pick m different features that best describe the model outcome, the complex model outcome from that permuted data. And if we are able to obtain this simplified or this smaller set of m features, we can try to fit a more simple model on those features. Like we take our permuted data, we take those features and the similarity scores, so how close one sample, one permuted sample is to our original observation, take those scores as weights, and those feature weights that we'll learn on this simple model then can serve as explanation for a particular observation on the local scale, so for this particular example. Summing up, the underlying idea is change one sample and watch what happens. And if we do this in a clever way, Lime is showing us one way how we can do this, we can actually get some really good insights into our model and see how changing our input, what effects it has on our output. Let's take another look at an example how we can use Lime for our own problems. We are now back in our Google Colab notebook, and as you might have guessed, we are working in the image domain here again because it is the domain that is easiest to understand and explain here. This is an example that is adapted from this resource, and what we're doing here is now taking this Lime and applying it to a similar problem that we've seen before. So we're doing again image classification. This is our image, and we're again doing some input transformations to get that model into the same shape how the network was seeing those samples during training, so some normalization. And then we can call, so there you go. We get some predictions. In our case, it classifies this image as a golden retriever, which is the most likely, then cocker spaniel, plumber, and so on. And we would like to understand which parts maybe led to those explanations. So what we do is we define the method how Lime can instrument our model. This is something that you will always have to give Lime because it's able to work with black box models only because it can play around with the model, and this is exactly how it's playing around with the model. So you have to give it a method how it can perform predictions on perturbated data. So we have to define this batch predict. And then what we do is we call this Lime implementation here, which is this framework, and we see that these are the regions that it thought are most important for making certain decisions here. So we can get these masked boundaries here that the model was taking a look at and trying to understand why it made a certain decision. In this case, a golden retriever. So it obviously looked at the head and similar parts here from the body, which makes sense to take a look at those parts of the image to make an image classification decision. A similar yet slightly different approach is RISE, but the difference now being that instead of permutating our input data, we are masking it. So we have a common prediction. In this case, the network said 26% this is a sheep and 70% cow. And I agree, those are quite uncommon pictures maybe of sheep. But we would like to understand, why did you say that a cow is 17% likely in this case? So are cows and sheep the same for the model? Or what was giving it this reason? And RISE is trying to create some saliency maps similar to what we've seen before, but allowing us to do it on a black box model. So it creates these importance maps that measure how salient each pixel is for the model prediction by randomly masking out certain areas from our input and then measuring how much the prediction changed. And if we do this, we can see that once we mask out the left instance here, the left sheep, we will get a prediction cow, and if we mask out the right thing, we will get a prediction sheep. So we can kind of say, well, okay, apparently this left part here is why the model predicted sheep, and the right sheep here was creating this prediction of a cow, probably because of the color and the shape and so on. So this is also a quite interesting model that you can play around with. RISE. When we leave our domain of visual computing now, we can also take a look at reinforcement learning and how we can learn finite state representations for recurrent neural networks in those reinforcement learning situations. The problem that we most of the time have is that we can learn a policy, but the policy that we use in our reinforcement learning problem is very complex to understand. It has a large internal state, and we don't really know immediately how it's using the inputs, how much it is using its memory. So if we were able to extract a more simple explanation, that would really help. And this work, they showed that you can actually learn a much simpler representation of your model, namely a Moore machine that reflects the policies that are being used for these Atari games that I showed you in the previous lecture. So it would be great to understand that internal state, and if we can map our complex state onto such a simple state machine, it is much easier for us to understand this. Obviously, those simpler models, those state machines, also have to perform equally well. So the question is, how do we get there? And we would like to answer these questions like, is it using the observation input, or is it just remembering that if I saw this, 10 steps afterwards, I should do that? So how are states encoded here? And by understanding those states, we can explain much better what the model has ultimately learned. So let's take a look at how you can actually transform a trained model into such a more simple space. And if you don't know if you've forgotten what a Moore machine is, it's a state machine that has our outputs on the state. So whenever we enter that state, we output something, and basically the states define our outputs. The method how you can do this is called Quantized bottleneck insertion, and it combines many of the things that we've seen in this lecture. Now, this is the cool thing, that you now should be able to understand all those different building blocks that are going on here. What you're doing is you are employing a basic autoencoder. We already know autoencoders. They take an input, transform it, ideally into a simpler representation, and then transform it back in the decoder into the same output. Here is a perfect place. So we want to take our state space, our model, and want to map this continuous observation space into a finite and discrete observation space where we can reason and understand what's going on here much easier. How we're doing this is that we're quantizing our code, our hidden state code, to k levels. If we have k equals 3, then we would quantize the value to be either +1, 0, or -1. And if we kind of quantize it to these 3 states only, we can kind of interpret this as a state machine. So to keep this differentiable, this quantization, the backpropagation just ignores quantization and treats it as the identity function. So the Moore machine network that you can ultimately build here can be seen as a traditional recurrent neural network, but the memory is restricted to be composed of these k-level activation units. So we're no longer operating on this continuous observation space, but we can only have these 3, if k equals 3, 3 different activations. And our observations are transformed immediately to this k-level representation. The algorithm to obtain these is the following. We start off in stage 1 with our regular machine learning model where we train our policy with some sort of recurrency, so we get a trained recurrent neural network. What we're doing now in the second stage is that we define 2 functions here, autoencoders for f and h here, that transform, like going from our input representation to this simpler activation, this simpler space that only has 3 values, and then having the decoder come back to the original values here. So we use these 2 autoencoders instead of ft and ht of those functions, and then we just insert them here. And we then take those ft hat and ht hat, those simple representations, those bottlenecks from the autoencoder, and interpret them and try to work with them. So that's the idea, that if we now insert this quantized bottlenecks, we of course lose some accuracy potentially. That's why we might need some fine-tuning, but you can see how inserting autoencoders into such a network can help us to get to a smaller and more interpretable state space. The next topic we're going to take a look at is generative adversarial networks and how we can dissect and take a look at them. Last year I had one student who gave me permission to use this great figure in this lecture here. What he was working on was creating new Pokemons, with the underlying problem being that there are already many Pokemon and it becomes increasingly harder for the creators, for those artists, to come up with new Pokemons. So he had this idea, well, let's just train a generative adversarial neural network to draw and come up with new Pokemons that look as if they were actual Pokemons. As you can see in these examples here, well, they might be a bit of kind of, he coined the term Chernobyl Pokemons. But it is really interesting to take that model and ask the questions, what knowledge went into this? So kind of you can see the foreground, background being either the background being black, white, or maybe one color. So there's this concept of background color, and then obviously the shape and the color of the Pokemon itself. So maybe it would be interesting to understand what caused some mistakes here and what is the fundamental difference that is encoded in the weights. For example, this black-white background. It must be somewhere in there that a particular neuron said, well, please give me white background or give me blue background. The work I'm going to discuss here with you now does the following. So when you remember one of the earliest lectures, one of the first few lectures, I said that neurons in late layers, so towards the end of our neural network, respond to specific high-level concepts. And this work actually proves that this is indeed the case. And if you have a neuron that is responsible for the background, if you have a neuron that is the kind of grandmother neuron that activates whenever you see your grandmother, then you can take that particular neuron, activate it or deactivate it to get a certain reaction. So if we can identify these individual neurons and find a causal relationship of what concept they relate to, it would allow us to work in such a way that we can replace inputs and directly say, I want to see the same Pokemon, but instead of with a black background, I want to have it with a white background. And you just change that one neuron because it corresponds to that particular concept. This is a wonderful little demo here, which shows an image, and you can, so it learned some concepts here: dome, brick, cloud, sky, door, grass, and tree. And now that we know which neurons correspond to these, we can say, okay, I want, in a certain area of my image, I want concepts to appear or to disappear. So let's make our sky clear. So I want to remove the clouds here in that sky. Okay, let's do it again. Still some clouds. Okay. Maybe let's try the other way around. Take another image that has no cloud and draw some clouds. So there we get some clouds. Maybe we have a big cloud here. Okay. It sometimes works better, sometimes works not as good. This is a funny example. So it created sky here, so we can draw some sky over here and therefore remove the top of that building partially. We can, let's go to another example. Draw some doors or draw some trees. I think this is a nice example. So there is just one tree here. We would like to have a bit more, so maybe a tree here and some trees here. And this is a lovely example how you can kind of add or remove features. So let's remove this tree here. And it amputated the data in such a way that it now generates something that more looks like a continuation of this building instead of the tree. The question that you obviously gonna have now is, how does this work? And the answer is that you do the following. You generate some images. That's what your generative adversarial network is doing. And then you try to identify objects inside a network that correlate to certain objects. And how you do this is you generate a sample and you take a single unit, single neuron here. You take a look at the feature map of that neuron where it activates, and you upsample that to your entire image and threshold it. So you can say, okay, it was very active in that region here. And what you can do also is take that generated image and run an image segmentation algorithm. What the image segmentation algorithm will do is it will put a label onto each pixel and say which concept appears at that region. So we have, in this case, a neuron that activated at the top of that building, and the segmentation might say, well, in that area there is the top of a church, and this agreement you can measure by the intersection of a union, and therefore start to learn which neurons correspond to which concepts. Now, if we think this a little bit further, and we've identified those units, we can force them up or down. We can say, okay, you are the cloud neuron. So if we enforce that neuron and activate it, we can say, okay, we want more clouds in that particular region of our image, or we can kind of decrease the activation of those neurons and then ablate them. And we can also do this and see if there is a causal effect between a neuron increasing and decreasing that by measuring how our image segmentation changes over time. One more thing that is quite interesting here is that we can also learn where certain concepts can appear at all in the image. For example, drawing a cloud at the bottom might not make any sense at all, because then the image segmentation algorithm will say, no, there's no thing here, or drawing grass in the sky. The final topic I want to explain to you is SHAP, or adding the question, how does this add up? The idea of SHAP is, the name stands for Shapely Additive Explanations, and it was originally motivated by trying to predict the risk of hypoxemia. Hypoxemia is an unusual level of oxygen in your blood. And the situation where this research came from is that when you're undergoing surgery and when you're in the hospital, you are being monitored by a whole bunch of instruments. You're wired up to many different machines that constantly give some measurements, and you want to predict in advance how likely it is that a patient suffers from hypoxemia in the next 5 minutes. Because if you can predict that, you have much more possibilities how to react as soon as possible to mitigate the risk of the patient suffering from severe damage. So we would like to have this prediction, because some medication can actually take some time as well before it becomes effective. So that's the initial problem that they were facing, and what they're doing is here they want to understand how each feature that they monitor and that they know about a patient adds up to the final prediction of a model. It's a technique to explain exactly those individual contributions by explaining the output as a sum of the effects of each feature introduced into this conditional expectation. So we reframe the problem and say, okay, we hypothesize that each feature that is being fed into our network either increases the value or decreases the value. And we would now like to understand how much it contributes to our basic output. So what we do is we compute the base value from this expectation here of our model, and then we try to explain how to get from the base value, kind of the average, to a specific observation. And this assumes independence of the input features and computes the conditional marginal distribution. So we say, okay, given one input feature, what is the expectation of this conditional distribution now? In this diagram, you can see one ordering of, say, okay, well, first take that feature into account, then this feature, and then that feature, and then try to come up with the basic values, that how much they contributed to this. Of course, when the model is non-linear, the input features are not independent. So what happens with those SHAP is that they compute those 5 values and then across, and basically average them across all possible orderings. So it's a connection between game theory and local explanations in such a way that the Shapley values is a method for assigning payouts to players depending on their contribution towards the total payout, which is exactly what we want here. We want to understand how much each feature, which in our case would be the player, contributes in our game, which is this prediction task. And the gain is the actual prediction minus the average prediction, this base value that we have. So every patient has a certain risk, a base value of suffering from hypoxemia, and certain features that we know about them, like maybe they're obese or have some other conditions, contribute in a certain way to that risk. And if the risk has a certain level, we know that the patient might suffer from hypoxemia. So the Shapley value is the average marginal contribution of each feature over all of these coalition, and by coalition I mean the combination of features. And for nonlinear functions, we would like, in our case with neural networks, we have nonlinear functions. The order matters, so we have to average over all of these possible orderings. And in their work, what they show with their implementation of SHAP, that you can do this quite effectively and efficiently. And let's take a look at another example here. This is the last example that I have for you, and it shows how SHAP can be used. The library SHAP that has already implemented all of this underlying idea of how we can assign individual features to certain contributions. So what we're doing here is image classification. MNIST, the website where this is from, also has lots of examples for other problems, but as we know, MNIST is kind of the hello world. So let's train a simple neural network, simple convolutional neural network here for 12 epochs, and then see what explanations we can get from it. The model has now completed the training. We get a quite good accuracy of 99% with a simple 6-layer model, if I see it correctly, or no, actually it has fewer convolutions, so just 2 convolutions, so it's working already very well. And we can now use this deep explainer here and feed in our model and run some samples through. And what we have now for images is that our input features are pixels, obviously. So we want to get these SHAP values that basically say what is the likelihood of that class given that pixel here has a certain value. So we get for the input number 2, those 10 numbers here are the probability for each class. And you can see that obviously the red areas increase the probability of that class and the blue area decreases the probability of that class. See that kind of those parts here were interesting features for making the decision of a 2 and maybe this for 0. Seeing also that the middle part of the number 0 is important, that this has to be empty for it to be a 0. Maybe something that is also interesting here is 9 and 4, because they share some features, and you can see that the probability of being a 9 is negatively correlated to this part here being empty. So you can see that for saying this is a 9, we would need some information over here, which we don't have. That's why we say it's a 4. And it also pays a lot of attention here at this part. So this is how you can use SHAP for simple image classification models. Summing up today's lecture. Interpretability is the passive characteristic of the degree by which humans can understand the course of a decision that a machine learning model took, whereas explainability is the active characteristic of a model taking some action to clarify its internal functions and the output. The most important goals of explainable AI include informativeness, fairness, privacy, and reliability. And you remember also there are some other goals, but those are, I think, the most important ones. Explainable AI can be achieved by either having a transparent model, by using something that is intrinsically explainable, like a decision tree that we can understand quite easily and simulate, or by using some post hoc explanations. And some of the techniques for performing these post hoc explanations I showed you, like having this Saliency Maps, Lime, Rise, or SHAP.